All right, welcome back from lunch. Hope everyone enjoyed the weather outside. I think going forward, plan not to leave this hotel until Thursday morning. Coming up next, we have Lee Howard moderating a panel talking about the IPv6 performance bonus over IPv4. Lee Howard.
Thank you. Good afternoon. I'm glad everybody could be here this afternoon. So I had this question a little while ago that I asked, and it was an interesting question of what's the, we're running v6, we're running v4. How does IPv6 performance compare to IPv4 performance? It turns out to be an interesting question, by which I mean the answer raises more questions than it answers. So as I was talking about the fact that IPv6 seems to be faster, which is, by the way, the spoiler alert, IPv6 seems to be faster, I talked with other people who said they were finding the same thing. And so I've invited some of these people here to talk about how they're measuring the comparison of performance between v4 and v6 and what results they come up with. Completely different methodologies, so pay attention. If you think you know why v6 would be faster than v4, see if your theory holds up as you hear how each of us has tested. I'm going to have Jeff Houston go first because he apparently needs to dash to catch a plane. Jeff.
Thanks, Lee. I should note back home the temperature is 39 degrees. And that's Celsius, not Fahrenheit. And I've never seen sleet in my life, and I don't intend to. Who's got the slide machine? I do. So in my measurements, I've been actually perverting Google ads and looking at the network from the outside looking in. Because inside the normal ads that you see in pop-ups, you can actually embed code, flash code. And in that flash code, you can actually direct the user to retrieve URLs from a server of your choosing, or in this case, my choosing. And the ad gives the user a very simple and quiet background test. It's a dual stack end client, and if they are dual stack, I'm going to ask them to fetch a v6 only object and a v4 only object. And I do this around 500,000 times a day. So everything is packet dumped. Everything is logged. I've now got a huge amount of data around folk fetching things in 4 and fetching things in 6. And for 2% of you, I can match you up. I know your v4 performance and your corresponding v6 performance. But before I actually look at raw performance, I want to look at connection reliability. If any of you have ever used Teredo or 6-4, you will have realized that sometimes the packets just don't make it. And it's not obvious how they don't make it, or maybe it is, but the symptom is pretty easy. At the server side, you send me the opening SYN of a TCP. I see your packet. Now, because I'm an obedient kind of server, I immediately answer you with a SYN-ACK. Saw you, here's my SYN. Some of you never respond. And the typical reason why is you have an inbound filter that says, I don't like your response. I don't like v6 for some reason. So I start to measure this every day. Since July 2012, I measure this. Red is v6, green is v4. v4 has a failure rate. And that's predominantly, as far as I can see, bots and scanners who send me SYNs on port 80 just to see if I'm alive. And they don't bother completing the handshake because they don't care. They just want to see if I've got something on that address on port 80. So that's normal. What's v6? Well, hell, it's between 1% and 3% every day of connections that fail. Let me get that again. That's 1 in 50. So if you had a service that you sell to your users that doesn't work for 1 in 50, what's your commercial business proposition look like? You know, this is not good. This is a visible proportion of IPv6 capable folk who are perfectly capable of sending the packet but aren't listening to the response. They have incoming filters. So I can do some work on this, and if you look very carefully at the slides online, you might find yourself on that list. Is there anyone here from Edgecast? Because if you are, you should be somewhere else fixing this, because your failure rate's 95%. It's amazing. I see a few others in there too. You might yourself look online, look at the list in detail. I also have a look at my Origin AS by the largest. Janet do a lot of work for us. Janet's rate of failure is around 1.2%. That's not bad. Comcast, 1.84%. And don't forget what the implications are for failure, and let me go through this very quickly. If you're running a Windows box and you get back an A and a quad A, the first thing you will do is try V6. Now for 1 in 50 in Comcast, that's not going to work. How long does Windows wait before it reverts to V4? 21 seconds. So 1 in 50 sitting behind those networks, when they go to dual stack URLs, performance becomes like molasses. 21 seconds is an eternity in user space. If you think about the $1 million millisecond, how much is 21 seconds worth? So the next thing for the US and Canada nets, go and look online. You might see yourself listed there. Time Warner is there, Comcast is there down low, but there are a few others. Yourself might be listed there as well, including Akamai, by the way, and Hurricane Electric. So see if you can find yourself. When I move on from there, there's a second part of this measurement, which relies on the fact that the TCP SYNAC handshake happens at the kernel. You can't, as a user process, slow it down. So when you send me a SYN, you've set up a PCB state in your kernel going, waiting for the ACK, waiting for the ACK, waiting for the ACK. When I send it back, you immediately close the handshake. There's nothing you can do about it. So if I measure the time between the SYN and the ACK, I've got a relatively good RTT estimate because there's no user process in the middle. And of course, I'm sending you both a V4 and a V6 experiment. So I can do this measurement for V4 and V6, and then I've got a paired measurement. The RTT from you to reach me, and in your case in America, I'm in Palo Alto. If you're in Europe, I'm in Hamburg. I'm relatively close to you. So I've got a relative measurement of those RTTs in 4 and in 6 that works for both V4 and V6. So I measure the elapsed time between the SYN and the ACK. So what do I see? That's the RTT distribution in July of 2012. Now the middle line is it's the same. Out there is 2 times, and that says, for example, if it's on the right-hand side, V4 RTT was twice as fast. In other words, half the V6 RTT, and so on. Down the left-hand side, which is slightly more sort of less populated, you'll see that a number of times the V6 RTT is better. And so it even gets as high for a couple of measurements out at 3 times. That's the profile in 2012. And the real question is, has it got any better? So I did the same profile in December. And I think you could all agree, couldn't you, that the distribution of ratios of V6 to V4 has shifted to the left. But what I'm actually seeing for a lot of folk is the V6 RTTs are coming through faster, with actually a curious peak at around 1.5 times faster. Now, there are certain theories about why. And I must admit, I find this getting into a difficult area to understand. I suspect that part of this issue is we are experts at deploying network middleware. And if we're going to look at a SYN packet, the bread and butter of this network is SYNs on TCP port 80 in V4. And I suspect you deploy a lot of software that is keenly interested in SYNs in TCP in V4. And you pick it up and look at it and then drop it back on the wire. And my suspicion is you're not doing that in 6. So part of this might well be a middleware issue, that there's a lot more active middleware on port 80 in V4 than V6. There also could be issues in the forwarding plane, but I'm really not sure how that affects things. And that is an area of much further work and much further research. So that's the basic scenario of what we've been able to do in APNIC. I don't know if you want questions now. I will be running, so if you have some urgent questions for me, you better be quick right now to the microphone. Thank you.
Hi, Daryl Newcomb with Scenic. Jeff, you mentioned, I maybe misheard you, just 2% of the results were paired? you had samples from a lot, and if I heard correctly, it was just 2%.
The total global deployment of V6 coming out of our experiment is around 2%. So across the world, when we give out 500,000 ads a day, just 2% of them actually manage to do the V6 dance. So yes, it's a low number still.
Okay, perfect. Thanks.
Thank you.
Hi, Leo Wicklow for
Hi.
Security. Two kind of questions about your methodology. I assume that you have used a mechanism that avoids any happy eyeball code in the client to do these measurements, because I'm wondering the behavior you see where a V6 sends and doesn't reply could be happy eyeball code sending two sins if you don't avoid it.
The issue about happy eyeball code actually happens when the DNS returns an A and a quad A for the same answer. The experiments that I'm doing explicitly refer to those URLs where there is only a quad A and there is only an A for the different URLs. Because I'm aware of the happy eyeballs and the caching and all the other issues. The URLs are unique. There are no caches out there. I'm looking at the raw performance between you and my server.
Sure.
Nothing between, in theory.
The other question I had on the graph you just showed is, could you actually show the same, obviously not right now, but on your website or something, the same graph with the actual RTTs? Because for instance, if you're in Palo Alto, the difference between 1 and 2 milliseconds may be kind of meaningless, but the difference between 60 and 120 is gigantic, and they're both 2x.
Correct. We had a lot of trouble in trying to figure out how to present the data, because I get data from Africa, Greenland, and all points in between. And when you talk about absolute differences, where you are is as relevant as the relativity. And the relativity, removing the absolute, seemed a little better. And that's why we get the big outliers. It's the folk who are very close that have a few milliseconds of difference. So there's a lot of measurement noise inside those figures. What I was trying to say is the big picture has just moved slightly.
Sure.
Just a little.
What I might be curious to do is run the exact same analysis by bucketing in like 5 millisecond buckets the data, so minor differences disappear.
We should talk about that. It might make a fun presentation. Thank you.
Thanks again, Jeff, and I hope you have safe travels. So that's exactly the sort of thing that I'm expecting to have a lot of conversation as the rest of us finish our presentations. Is I'm certain that everybody's going to have ideas for further experiments that we ought to conduct and further ways to analyze our various data, because it does seem to be raising additional questions. When I went to measure from my network, again, my question was, how does IPv6 performance compare to IPv4? And I built a dashboard. And I have to give credit again to John Brzezowski. This was an idea that he'd given me. I basically took a probe. I have a server in each of 10 different hubs. And don't worry, I'm going to zoom in on this slide in a minute here, so you'll be able to see what's actually represented. But the column headers are the hub name, and then the row headers, right now I just have letters because I don't want you to see the actual performance to actual websites. I don't want to call anybody out in particular. And what I've done is, for each hub, I have a server that sends a v4 and a v6 connection, and then I've got the v4 round trip time in milliseconds and the v6 round trip time in milliseconds. So what this does is then I can, and if there's a 30% difference, then I color it. If v6 is 30% faster than v4, it's colored green. If v4 is 30% faster than v6, I color it pink. Why 30%? I chose that arbitrarily because that seemed like significant. And you can see sort of the summary of results here. So along the bottom, if you want to zoom in on these slides later, download them and look at them yourself, you can see that our, the average speed by hub, and I've got on the right average speed to each site. So what I've got, the top row there is website A, which is dual stacked, and I've got performance measurements to each of those sites. If I take an average of all of these results, I get the average IPv4 performance is 39.3 milliseconds, and the average IPv6 performance is 33.4 milliseconds. That was at the time that I took this particular snapshot of our dashboard. So that's still, and that's been fairly consistent over time, is that v6 has been faster. Let me zoom in so you can get a better sense for what I'm looking at here. So here's, I've got from one of our LA hubs and a New York City hub, and I've got website A, website B, website C, and so on. And you can see that website A is not doing quite as well over IPv6. Website J doesn't look very good over IPv6, but all the rest of them look better over v6 than v4. So what's the difference here? And I've got an average and a 95th percentile to try and normalize a little bit against the difference in distance. So what I find is, in general, either a hub is doing very well or poorly, and a website is doing very well or poorly, and there are indeed generalizations that I can make. And one of the things that I keep seeing, for instance, and I want to be able to dig into some of the numbers that I'm seeing, is this website J is consistently worse over IPv6. So why would that be? Well, one possibility is that it's taking a different path. And that's something that Jeff mentioned is, gee, maybe there are different routes that the traffic is taking. Well, obviously, that would cause a difference. But that second to last row in black there is website J, and you can see that the hop count is shorter over v6 than it is over v4. In fact, it's more than 30% shorter over v6 than it is over v4. Why would the latency be higher if the path is shorter? Tunnels, of course, yes. So obviously website J is doing tunneling inside their network. And I went to, if you go to Eric Vinke's website listing v6 enabled websites, he does indeed say that website J is one of those that is tunneled. So, and I've confirmed that with engineers there. So there you go. Tunneling turns out to have not as good performance as native IPv6 connectivity. Shocking revelation, you heard it here first. In general, the other sites, there is a fairly close correlation between hop count and latency, kind of as you'd expect, but it's not as direct. I haven't been able to, over time, compare the different routes that things are taking because that's the amount of data and how to do a comparison of two trace routes as they change over time is, I haven't been able to wrap my head around that model. But I can look at the average round trip time and how that changes over the course of a week. And I can do this hop count too. So any statistic I have, I can go look into the history of that. In this particular case, this is average round trip time in milliseconds. And then, of course, the x-axis is time. And blue is v6 and pink is v4. And you can see that for the first half of this week, v6 was spiking a little bit higher, but the baseline, v6 and v4 were pretty much about the same. And then something happened midweek. The route changed. We don't know why exactly. And all of a sudden, the v4 performance degraded and was a lot higher. v4 was a lot slower. Well, why is that? Another trick. I don't know. There are lots of possible things. You could, if you had data like this, you could try and go correlate to trouble tickets in your ticketing system. I think you would probably find that more often it's something's been rerouted through a CDN has done something different, or the content provider has rerouted traffic, or there's something strange going on outside of your network rather than inside your network. That seems to be the case for me. By the way, I don't think I ever pointed out that all these average round trip times are almost exactly the same methodology that Jeff has. We had originally started to implement it as an ICMP, just a basic ping, and we said, gee, ICMP maybe isn't the most reliable way to see how the internet's working. So it's TCP, you send a SYN, you wait for a SYNAC, and you count the difference, and that's your round trip time. But I'm not sure that that's the best way to measure, just because the round trip time for a SYN and SYNAC is a certain speed doesn't necessarily mean that that's your actual page download time. So in order to try to compare page downloads, we also look at curl-4 and curl-6. So here, you'd rather see a higher line. Again, v6 is blue and v4 is pink. You'd rather see a higher line because that means a higher speed. I will point out that because I had a tools developer build this tool, the measurements here, the y-axis, is measured in kilobytes per second rather than in kilobits per second. A network engineer would have used kilobits per second. But the point is, two interesting things I think about this chart. One is v6 performance is generally faster than v4. And in fact, the worst v6 performance is about the same as v4 for this website from this hub over this time period. That's pretty interesting. But the other thing is, it's really spiky. The v6 performance changes radically from sample to sample, and I have no idea why. That is true for this particular sample, but that's not true for all of them, and I can't generalize that to any other statements. So unfortunately, the conclusions that I have are, I can conclude that of the sites we're measuring, IPv6 is generally faster. I can say that's not always true, or it's not consistently true, from 4 sites that tunnel v6 over v4, because it's tunneled. And it's not true for our hubs that are not necessarily the closest exit. So if there's a better exit and traffic is being routed suboptimally because of a content provider or CDN's traffic engineering, then maybe the performance isn't going to be as good. I can't reach any conclusions about variability. They both vary, and not according to any pattern that I've seen. But the biggest thing that I can say is that more research is needed, and I expect this is something we're going to want to keep paying attention to. I'd like to take questions, but I actually think I'm going to hold questions until John and then Chris have had a chance to go, because some of the questions that you might have for me will be answered by the tests that they've done, and then we'll see if we can wrap up with the most interesting questions that we can find. So, John.
Thanks, Lee. Hello, everyone. Long time no see. Let's see here. How do I work this thing? Green arrow. Green arrow. Got it. Okay, so years ago, when we started to do our thing at Comcast for V6, one of the things, and truth be told, the genesis of this work and this data was actually not to determine whether or not V6 was faster. It was to prevent myself from getting fired. So, early on when we started to roll out V6, the folks that I work for were like, so yeah, go ahead and deploy V6, just don't break anything. So I was like, yes, sir. Thank you, sir. No problem. So what we did is we went ahead and we basically built a series of test tools initially that turned into validation tools and audit tools, all leading up to essentially World V6 launch a couple years ago, whenever that was. And the goal there was to make sure that if anything went awry, either on the Comcast network or essentially on the internet, that we weren't the last to know, because that's really awkward when folks in your markets call you up and say, hey, call center volumes are spiking, and what the blankety blank is going on. Very awkward situation. So what we did early on is everything from some pretty basic tests that oriented around ICMP. Which over the years really grew into a series of homegrown tests, and then in more recent times, we even leveraged some commercially off the shelf software and other open source packages. So we essentially built a suite of tools and have been able to trend data for really many years now that tells a lot about how V6 is performing. One of the things that I'll share with you from the earliest days is probably going back 3 or 4 years ago. When we first started to do some of the trials for residential broadband in V6, some of the folks that were doing some of the testing and seeing some activity in the field came in and said, hey, V6 looks like it might be faster. And of course, me being the guy that was running the program, you can imagine what I wanted to say, but ultimately what I said was, it can't be true. And we all, I kind of chalked it up to, this is an anomaly. But then systematically over the years, it really started to appear more and more. So conveniently, we started to collect a bunch of data. So the data that we collected basically orbits around what you see here on the screen. These used to be red, but Lee mangled my slides. So we basically decided that early on that in order for us to really dissect this and understand what aspects of the network are performing in what way, we really had to break this up into more bite-sized chunks. So on one hand, we take and we measure and we test the broadband network, right? So the stuff that makes cable broadband networks go, cable modems, CMTSs, e-routers, and the like. Probably the longest two pieces that we've been testing here are the pieces that are essentially the core networks. So when we run tests between regional networks, we expect that to be pretty, predictable and consistent. And then of course there's stuff that goes out to the internet, and this was the piece where all this originally started, where we said, hey, wait a minute, if our tools report issues, then our customers are probably having problems as well. We kind of ball this up into essentially what we call an experience index of sorts, and it really is trying to simplify what this data means, so that when we talk to a wide range of people in the company, we can kind of uniformly communicate what we think the performance is. So a couple of things that we've observed over the years. So that was a bit about the methodology. Over the years, and more recently, we've noticed that when we kind of run V4 and V6 tests side by side, in the kind of the isolated environment where the broadband components are kind of in play, we noticed that in some cases maybe upstream and occasionally downstream V6 outperforms V4, but they're largely in parallel, right? And this is unfolding as we speak, literally. There's actually a couple guys in the audience here, Tony and DJ, that have been hugely helpful in making this happen. So this is something that is really ongoing for us. It's something that we hope to come back here and be able to share more information around. But ultimately, one of the things that we've kind of came to the conclusion is that, the chipsets, the underlying implementations, they really do matter, particularly when you get into the home, the customer's home. And we also kind of, I don't want to say hypothesize, maybe guess is a better way to put it, that the fact that a lot of these implementations are newer, maybe they're not riddled with hacks as much as V4 is. And frankly speaking, from a deployment point of view, V6 has always been a lot simpler for us from a deployment point of view, as far as the kind of the broadband network is concerned. On the core network side of things, we're seeing again that a lot of performance is pretty even there. It's largely even across typical scenarios, right? So we're not talking about scenarios where MTUs are adjusted. We're talking about just steady state, moving back across from regional network to regional network. We do believe, however, that based on some kind of preliminary test that with some optimization around MTU configurations, there is an opportunity there. So a little bit more on that maybe later. So here's where we saw the greatest variety of things, right? So when we do kind of the internet-facing measurements, right? So if you kind of get inside of our head, we're trying to break this down into bite-sized chunks. We got to take into consideration things like DNS lookup times, connect times, and transfer times, right? What we really tried to do was simulate as best as we could in an automated fashion what a customer would experience. So what we noticed, over the past few years is that CDN readiness and availability specific to V6 played a huge role in this, right? In some cases, some of our customers get served out of some pretty strange locations, which in the early days meant that V6 was certainly slower than V4. A lot of that has changed over the years. But on the flip side of that, there are a lot of content providers that have done an impeccable job kind of making sure there's parity between V4 and V6. In many of those cases, we actually see V6 perform better than V4. And of course, there are also cases where people who don't leverage a third-party CDN and host their own content, we've seen that, basically, we've seen some pretty severe train wrecks on that front. A lot of people who simply just plug it in, walk away, don't do any tuning as far as the last hop router is concerned, as far as the server. We've seen some pretty bad performance, and that continues even today. The folks there will remain nameless, but to the extent where V6 almost looks broken to our customer. So what does it all mean? Well, so here's the very strange part. So for the past year, maybe more, and DJ will keep me honest here, we've had dual stack our speed test servers enabled for dual stack. The bulk of the data, when you start dropping highs and lows and taking averages, we're seeing that V6 data, the V6 performance tests are actually faster than V4. So going back to Lee's point, why is that? If everything else has been pretty congruent, then why we're pretty like or similar as far as performance are concerned, why would there suddenly be speed tests performance differences? We do have a pretty significant sampling size. 30% of our customers are actively provisioned with dual stack enabled broadband. All of our speed test servers, to the best of my knowledge, are dual stack enabled. Yeah, I'm getting the nod. Keep me honest. So we have a lot of data. This isn't like we're running one speed test server out of a lab in Philadelphia, and it's everybody in the Comcast center running speed tests. It's really not that kind of a situation. So interesting data point, and certainly something that we are exploring internally from a kind of a research and analysis point of view to kind of see what other opportunities may lie ahead for us. So what is next? So we are seeing that when you kind of put all these kind of three approaches together, that there is a difference. One of the things that we'd like to see happen more is more tests that are run from the actual customer's perspective, not only kind of measuring the performance from the home or the customer to the operator network, but also out to the internet. And of course, there are a ton of additional variables, everything from which version of Wi-Fi are you using, are you wired or wireless, what else is going on in the home network, is the customer infected with the virus, you name it, that list could be 10 slides all by itself. And throughout this process, we're also looking for opportunities where we think we can optimize it and really kind of improve the experience for the customer in the long run. So with that, I actually might be on time. Chris?
Hi, I'm Chris Donnelly from Cable Labs, and I'm going to talk about some of the lab testing that we did last week during our interop. Cable Labs has been doing IPv6 interops on a quarterly basis going back to about 2009, and especially in the last couple of years, we've been seeing subtle but persistent improvement for IPv6 performance. We've done carrier-grade NAT testing, we've done tests to website, and we couldn't explain it, but in our results it keeps coming up that there is better performance for V6 over V4. So we had another interop last week, and as part of it we conducted testing to measure V4, V6 performance specifically with 3 test cases. One was native IPv6, no tunnels. We hand out a prefix down to the routers and see what the performance is like. IPv4 with 1 layer NAT, which is pretty common today where the customer might have a NAT. And then to simulate carrier grade NAT, which we may get in the future, we put a second router in to show 2 layers of NAT. So here's a little picture of our test network. It's pretty basic. That we had a cable modem termination system, the CMTS, in the head end with the test server plugged into it. And then in the home we had a cable modem, one what I'll call a home router, and one is kind of a SOHO low-end router, and then the test PC. And the variability in this is on the bottom router, the low-end SOHO router, we would turn off the NAT and turn it into bridge mode for some of the tests if we wanted to go from 1 NAT to 2 NATs. And so we ran mashed IPv4 and IPv6 ping tests throughout the course of the interop. The first sets were with the 2 NATs enabled, and the second sets were with just the 1 NAT. And we did it this way instead of having the carrier grade NAT in the core because we didn't want any path differences between V4 and V6. And we also did not measure the effects of traffic engineering or any peering. We kept it all contained within the lab. So 1 layer of NAT. Could this be the cause of the slower V4 performance? It sure looks like it from this. The mean for V6 is lower than V4. The median is lower. There is less variability. We did have 1 spurious sample, so the maximum time was a little higher for V6, but the minimum was lower. This looks pretty cut and dry, right? Let's see what happens when we go to 2 layers of NAT. Here we go. We would expect that this would make it worse, and instead they come out the same. The mean, the median are pretty close. V4 looks a little bit better in this. Again, the standard deviation still shows more variability for V4 performance versus V6. The min is still higher than V6. But what's going on here? We ran some statistical tests on the data that we got back, and we're 81% confident that the means are really identical in this particular case. In the previous case with just the 1 NAT, we were very confident that the means were different. So what's going on here? Really what we think is this is a difference in performance of the lower end routers. That some routers show better performance with NAT and with V6 than others, and so when we had them in combination, it smoothed out some of the differences. IPv4 NAT only in some routers will affect performance, these effects are relatively subtle. And we think other network effects, such as tunnels and traffic engineering and congestion, are likely to produce larger effects. We're measuring in the order of magnitude of a millisecond round trip time. If we add a tunnel, that'll add 40 milliseconds right there. Some of these other techniques can add far more than a millisecond. So with this, I'm going to turn it over to Lee for your questions. Thank you.
So we do have a few minutes to take questions, but as you're rushing to the mic, I want to highlight some of the high points of what you just heard. John has measurements from his clients, his users, to some dual stack speed test servers that show that V6 is faster. It's not leaving his network. It's from the home client device to an on-net server. I have servers, no NAT, servers in hubs going to live production websites showing that V6 is faster. And Jeff has JavaScript or some code, maybe it's Flash, I don't remember, some code in Google Ads going from clients to his servers located someplace off-net that shows that V6 is faster. And Chris shows that V6 is faster than V4 when there's at least when there's a one layer of NAT, but not when there are 2 layers of NAT. I have no idea what this means, and I'm hoping that rather than questions, somebody here can help provide answers. If anybody could, it would be Leo.
Leo Bicknell, Farsight Security. I certainly don't have all the answers, and in fact, I will guarantee you that there are multiple factors involved here. The double NAT thing I find particularly intriguing, but certainly many boxes have been shown to have different performance, either better or worse. But one I can shed some light onto is I've had the privilege of running dual stack networks now for about 10 years and dealt with many IP transit providers and their dual stacked learning curve, let's say. And I've noticed a very common scenario across, I believe, all of them. So while anecdotes are not data, I feel pretty confident in this one. And that is when ISPs get congested networks, which I know never happens, some good intentioned engineer goes off to solve the problem. And what I generally find is networks are engineered to take the best route. That's how they start. Everybody optimizes well. We're very good at it. And so when there is congestion, it is some exercise in taking a worse path for some of the traffic. Because IPv4 traffic is, I don't know, 99.999% of their traffic, these well-intentioned engineers generally go in and move some large chunk of it somewhere else, and they see the link is not full, and they go, I'm done. And this nicely leaves IPv6 on the best path because it hasn't been adulterated in any way. And so I'm wondering if your data actually shows what the optimum network could be if we all had enough bandwidth where we wanted it. To that end, the question I have for the panel, so it's not just a description, is in particular for the two of you who work for ISPs and are tracking this on many sources, have you tried to correlate this with your NOC making changes to your IGP or BGP session to see how many of the little shelf functions happen to line up very nicely with a well-intentioned engineer?
For me, the answer is some. There is a correlation. It's not a strong correlation, which is part of why I was showing the trace route hop count. Presumably, if you reroute suboptimally, that you're going to be adding a hop, and I figured that would show us the effect of traffic engineering. And in some cases it does, and I can see a correlation, but it doesn't seem to be. So that's probably some of it, but it's not all of it.
Well, so two things. One is, of course, they won't all be changes in your network for the
Right.
internet measurements.
Right.
The other thing I would say that I know a couple of networks do, and I don't know what percentage, I'd like some people to say, but I know several networks that have their IPv4 traffic in MPLS, not necessarily because they use it so much for traffic engineering, but because they sell L2 VPNs or L3 VPNs or all the other things we do, and have chosen not to put their IPv6 into MPLS. And so that is a second thing that could certainly alter hop count in many cases.
Could. I don't think that applies to us, but John.
I have a question here. My name is Eric Rosenberry. I'm from a company called iOvation. Actually, it's not a question, it's a conjecture. I'm wondering if it comes down to the end user's NAT devices. Folks that have older crummy NAT devices don't support IPv6. So it's just the newer NAT devices in their houses that support IPv6. So perhaps that explains some of the speed difference.
But you wouldn't be able to run a dual stack comparison for those.
Oh, I see. Your data was only like for like folks
data,
that would.
Yeah. Well, one comment real quick for Leo, if I may. So Leo, wherever you went, we do have some, we don't actively correlate that right now, but we do have some trended data that we might be able to go back and take a look at that. But some of that involves perhaps network changes. But I'm sorry, going back to you, Eric, I think it was. Sorry.
Yeah, so you were only comparing folks that had both IPv4 and IPv6, so it was excluding the whole set of folks that were just IPv4.
That's correct. In fact, it's even newer routers than that. They were routers that supported IPv6 prefix subdelegation.
Gotcha.
So they're no more than 9 months old, shall we say.
Gotcha.
And John, related to that, in your speed test servers, you're only comparing tests where V4 and you're only comparing tests of dual stacked customers. You wouldn't compare a V4 only customer to a dual stacked customer's performance.
Yeah, it's difficult to do that.
Yeah.
We have some data that shows. Yeah, so truth be told, what we do in some cases is we take some of those popular domains that are visited from the broadband network, and we use those to as the basis for a significant portion of the basis for measurement, because that's where our customers are going. So truth be told, a byproduct of this is the fact that we also have the luxury of finding out very very exactly which FQDNs from which providers don't actually support V6, and then of course for the ones that are dual stack we can actually compare, which is good.
Okay, being sensitive to time, I'm going to keep the folks who are in line now, and if anybody else wants to be at a mic, hurry. Who's next?
Sure. Don Bowman, Sandvine. So 2 comments. The first one is, this is also conjecture, but it's based on, as a vendor implementing some of these things, IPv6 should be slightly faster, and there's 2 reasons. One is it has simplified fragmentation processing in the data plane, and the second is IP options processing. And depending on whether you have a network processor-based device or a ASIC-based device, in both cases it'll go through a cut-through path that'll be some number of clock cycles shorter, whether it's easily measurable or not. Over 10 hops, it will add up to something you can measure. And the second is, we also do a lot of work with latency, and one thing what we found is latency is not actually a Gaussian distribution, and it doesn't make much sense to use a mean and a standard deviation. So we often compare 80th percentiles, but medians are also good, but there's nothing actually at the mean. It's a sort of a exponential curve. So.
Thanks. We may do
Can I make
an
a
ADSP.
comment? Can I make a comment? So Don, one of the things that we've also confirmed as well in conversations with some of our other vendors is that they've confirmed similar, almost very very definitively about their products, like as it relates to home networking equipment. Very similar statements that you've made. So that's partly the basis for what I think why we're up here. Right?
Our equipment is slightly faster on V6, for example, because of that.
Cool. That would help a lot if that explains it. Last question.
Tony, last question. Thanks.
Okay. Tony Tauber, Comcast. So yeah, I've been working with John on this and other people on the testing. And just to Leo's question about the path, the paths are congruent for us. So they follow the same low latency direct route. It's not V6 and V4 doing different things inside our networks.
Great. Okay. Thank you very much. Great.